once again, you have one more homework assignment that's due on Sunday at 11:59 p.m. as always. It's on groundwater, chapter 16. Your final exam in here is a week from Thursday, once again on December the 14th, between the hours of 1 and 3. Once again, that's not set by me, that's set by the university, and I am not allowed to move it. So we have to adhere to that schedule. So it is just a 5th exam covering chapters 14 and 16. I've said that before. There's nothing magic about it. It's not worth more. It's not comprehensive. It's not anything except for a 5th exam. The only thing that's different about it is it has 50 questions instead of my standard is 55 to 60. And these chapters are not that long. So it has 50 questions on it, so that's the only difference between it and every other exam that you've taken. There are 30 questions on chapter 14 and 20 questions on chapter 16 for the division of questions. So, and once again, if you want to do the extra credit that pertains to exam 5, that's up on Canvas. It actually comes from thermophiles at Hot Springs National Park in Hot Springs, Arkansas, which is a groundwater-related feature. Okay, any questions about that? All right, so today we're going to begin chapter 16, and we'll finish this up on Thursday. I do cut a piece of it out because with groundwater, you either cut it off or you go into a tremendous amount of detail, which will take more than 2 class periods. So since we only have 2 class periods left, I've abbreviated it a little bit. So chapter 16 is about groundwater. It's called a hidden reservoir, and that's because you don't see it. It is subsurface water. First of all, what is it used for? Water is a resource, just like oil and natural gas and sand and gravel from graded stream deposits and alluvial fans, and the hundreds of minerals that we use to make all the stuff that we depend on every day. So it's important to understand what a resource is actually used for, because you can't conserve it, you can't preserve it, you can't use it wisely unless you know what it's used for. So we talked in chapter 14 about surface water. That was water in rivers, streams, lakes, reservoirs, etc. And surface water is used primarily by industries and to generate power. So industries like the petrochemical industry, pulp and paper, these are industries that rely on a lot of water. Your utilities that provide you with electricity every day, those are your power companies. They rely primarily on surface water. So if your concern is conserving or preserving surface water, you have to look at that sector, because that's who uses most surface water. That's what it's used for. It's used either for industry or by utilities for power supply. Groundwater is different. If you want to look at conserving and preserving groundwater, you have to look at agriculture, because the major use of groundwater is the agricultural sector, because they use it for irrigation. So it's not that we don't use surface water for irrigation, but if you look at all the groundwater that's used, not only in the United States, but in the world, most of it is going to be used to irrigate agricultural crops. So if your issue is conserving groundwater, you don't look at industries and you don't look at your utilities, you look at agriculture, because that's who uses the bulk of groundwater. They use it for irrigation. The second major use of groundwater, and it doesn't even come close to irrigation. There is a big gap between these two numbers. But the second major use of groundwater is what we call public supply. That's the water we use. You use that water to drink, you use it to wash your clothes, you use it to wash your dishes, you use it to take a shower. That's all the water that you use, fresh water that we use for sort of like our daily lives. That's public supply. So that's the second major use of groundwater is for public supply. But those numbers, those two percentages are not even close. Irrigation is a big number compared to public supply. But the two sectors where you can really sort of make a dent in preserving and conserving groundwater are to look at irrigation, but also look at public supply, how we use groundwater as individuals. And you might say, well, you know, what difference does that make? Well, you can live without your cell phone. You might not think you can live without your cell phone, but you can really live without your cell phone. I mean, I didn't have my first cell phone. I was, 40+ years old before I had my first cell phone. Just, they weren't even around back then. So you can live without your cell phone, but you can't live without food and water. So groundwater, as it relates to irrigation of agricultural crops to produce the food that you need to live, and also the water that you need in order to survive, comes from groundwater. So conserving and preserving groundwater actually really is a pretty big deal, even if you don't think it happens to be. But food and water are the two main essentials of life. So groundwater is really important. So we're a little bit about public supply and about what we actually use water for. If as an individual you're going to be a good steward of conserving groundwater. Okay, which takes less water, taking a shower or taking a bath? Okay. On average, this is on average, okay? No, shower. Showers use less water than the bathtub. So, little known fact. So if you want to be a good steward of using groundwater, if you want to conserve groundwater, take a shower and not a bath, because showers use less water. Okay, this is on average, okay? This isn't, somebody who spends 45 minutes in the shower, every day with one of those, big shower heads that's about this big, then you got the jets coming out on the side. This is sort of like you do your average shower. So taking a shower actually uses less water than taking a bath. So taking a shower is actually a good conservation effort versus taking a bath. Okay, which activity that involves water do you do every day that uses the most water? Something you do every day that uses the most water. Very good. Flushing the toilet. You use more water every day flushing the toilet than anything else. And that includes taking a shower, washing your clothes, however much water you drink in a day. Flushing the toilet consumes more water than sort of any other kind of daily human activity, which doesn't mean you shouldn't flush, because flushing is important for hygiene, and there is nothing in this world that will make you sicker than coming in contact with water that has been contaminated with human waste. Most of the world's misery, we're talking about very contagious diseases like cholera and typhoid and dysentery. These are all caused by people coming in contact with water that has been contaminated by human waste. So the whole hygiene thing about flushing is actually critically important for human health. You know, the invention of the flush toilet, you know, not using the outhouse and actually having indoor plumbing, you know, where you could flush the toilet and that water could be treated. That was actually a huge improvement in public health, because it keeps you from coming in contact with that contaminated water. So flushing the toilet is actually a big deal. However, you may not know this, but the size of a flush is actually regulated by the government. If you go into an old house that has like the original bathroom, the toilet is huge, okay? These things are monsters. And you're like, wow, that's a really big toilet. And that's because toilets used to be that big. But in an effort to conserve water, the size of a flush is now regulated. So toilets have gotten a lot smaller than they used to be as a way to conserve water, because we use so much water flushing the toilet. Okay, also little known fact. So if you buy a really old house, you can't even replace that gargantuan big toilet with another gargantuan big toilet. I guess maybe you could possibly find one on eBay, but good luck getting past the building inspector, because you can't use toilets that big anymore because they consume too much water. So the size of a flush is actually regulated, but that's where most of your water goes on a daily basis. It's used to flush. So if your mother told you things like, you know, turn off the water when you're brushing your teeth, or, you know, don't spend 45 minutes in the shower, those things are actually really important, because it helps to conserve water. But compared to irrigation, we can only make a little small dent in what we do compared to looking at the amount of water that's used for irrigation, because that is absolutely huge. So that's just a little bit about you know, the importance of the resource. Okay, so what is groundwater and where is it? Okay, there's a very common misconception about what groundwater is and where it is. In that, and you particularly see this if you might see an article that's written for the general public. Groundwater is often referred to as underground rivers. There are no underground rivers. Okay, that is not what groundwater is. There are no big underground rivers flowing below the surface. Okay, that's kind of the common misconception of what groundwater is. That's not what it is. Okay, groundwater is subsurface water. It's located below the surface, and it's in the pore spaces or void spaces in rock and sediment. So it's subsurface water, it's below the surface, and it's located in the pore spaces or void space, so the space between the grains in rocks and sediment. That's what groundwater is. It's not very glamorous, and it moves very, very slowly. Okay, groundwater moves very slowly through all of the void spaces in rocks and sediments. So there are no big, vast underground rivers flowing along that you can tap into. It's just water in pore spaces in rock and sediment. That's all it is. Now, whether or not a geologic unit or earth material, and that means it could be sediment or it could be rock. It doesn't really matter if it's we're talking about loose sediment or solid rock. There are two properties that are going to determine whether a unit is actually going to produce groundwater. Because there's a lot of rock and there's a lot of sediment out there, but they're not all good groundwater producers. What we're interested in are the ones that actually produce groundwater. So in order to be able to produce groundwater, your earth material possesses two properties. And the first property is called porosity. It's called porosity. And what porosity is, it's the percentage, it's actually a percent. It's the percentage of earth material, that means sediment or rock, doesn't matter. So it's the percentage of earth material that is pore space or void space. Another term for void space is pore. So it's the percentage of earth material that is pore space or void space. So essentially here we have some rock, we've got some grains. This is a sedimentary rock because the yellow stuff is the cement that glues the grains together, probably either quartz or calcite. And then the blue, this is the empty spaces. These are the empty spaces, and that's your porosity, and the blue represents water. So essentially your porosity is how much water your earth material can actually contain, how much it can actually hold, because the only place you can have water is in the pore spaces. You can't have water in the grains, you can only have water between the grains. So that is called porosity. Now, if you look at different porosity values, we're going to look first at sediment, and then we're going to look at solid rock. Gravel and sand have porosity values of somewhere between 25 to 40%. Okay? What that means is that if I bring in a bucket of gravel or a bucket of sand, it's going to contain somewhere between about 60 to 75%, grains of gravel or sand, and between 25 and 40% porosity, which is the space between the sand and gravel grains. Okay? So it has a porosity of about 25 to 40%. Silt, which is smaller, has a porosity of about 35 to 50%. And clay, and this is what people find surprising, clay actually has the highest porosity. It has a porosity of between 40 and 70%. Clay actually has a very high porosity. It's not a good groundwater producer because there's another property that's more important than porosity, but it actually does contain a lot of pore space, which is why, anybody here own a cat? Okay, got a litter box? Okay, you don't put gravel in your litter box, right? You put clay in your litter box. That's what kitty litter is made out of. Why do you put clay instead of gravel? Because the clay has a lot more porosity, so it can hold a lot more liquid than sand and gravel. So that's why kitty litter is actually made out of clay. Now, if we look at solid rock, sandstone has a porosity somewhere between about 5% to 30%. Once again, it depends on how much the grains are cemented together. And limestone can have almost no porosity, but it can have porosity up to 20%. So limestone has porosity from 0 to 20%. Now, mud rock, which is compacted mud, has a porosity of about 0 to 10%, and crystalline rocks, such as granite, will only have a porosity of 0 to 5%. The numbers, the actual raw numbers, aren't that important, but these are the porosity values. But there is another property that is even more important than porosity. So you don't need a super high porosity to produce groundwater, because clay, which actually has the highest porosity, doesn't produce groundwater. Even though the porosity is very high, it lacks another property that makes it a good groundwater producer. So what you really need as far as porosity goes is you need something with what would consider to be an adequate porosity. And gravel and sand, sandstone and limestone, those porosities are good enough, okay? You don't have to be up in the 40 to 50 to 60% porosity in order to produce groundwater. And the reason for that is because the most important property that you need to produce groundwater is something called hydraulic conductivity. It's called hydraulic conductivity. Porosity is important because you need to have pore space for water, but what's really important is hydraulic conductivity. So what is hydraulic conductivity? It's not actually a physical thing. It's actually somewhat similar to discharge in that it's the solution to an equation. But for our purposes, think of it as the ability of earth material to transmit water. The ability of earth material to transmit water. And it's important because just having water in the pore spaces isn't enough. What you have to be able to do is that water has to be able to move from one pore space to the next. So it's not only how much water does it have, but can we move the water through it? And that's what hydraulic conductivity tells us. It tells us we can move water through this material fairly easily, or water will not move through this material fairly easily. And so that's why it's the ability to transmit water, it's the ability to move water through the material that's actually more important than porosity. A term that is often used sort of synonymously with hydraulic conductivity is permeability. Permeability is actually not the correct term. Permeability is a term used in the oil and gas industry because oil and natural gas are fluids just like water, but oil and natural gas have some very unique properties that water does not. And so in the oil and gas industry, they use the term permeability. In the groundwater field, we try to stick to hydraulic conductivity, but a lot of times you will see that term permeability. So it's technically not correct, but essentially it's two words describing the same thing. So if I want to produce groundwater, okay, if I want to go to an area and say, okay, can I drill a well? And can I actually pump water out of the ground? What I want is I want a unit that has an adequate porosity. Doesn't have to be super high, but an adequate porosity and as high a hydraulic conductivity as I can get. That's the key. Adequate porosity, high hydraulic conductivity. Because a high hydraulic conductivity means it's easy for the water to transmit. It's easy for the water to move through. So that's the combination that you want, is you want adequate porosity and high hydraulic conductivity. And so these are going to be the big four: gravel and sand, decent porosity, 25 to 40%, very high hydraulic conductivity. Sandstone, porosity 5 all the way up to 30%, very high hydraulic conductivity. Limestone, yes, there are some limestones that have very low porosities, but most of them have porosities up around 20%. So you've got adequate porosity, very high hydraulic conductivity. So if I go looking for water, groundwater, these are the units that I need to find: gravel and sand, sandstone, limestone. These are going to be my 4 major water producers. Can you get groundwater out of something else? Certainly. You can get groundwater out of a granite, which is a crystalline rock, which they do up in the Northeast sometimes, but it has to be fractured. It's a lot more complicated than if you have one of these, gravel and sand, sandstone or limestone. So there are other types of materials that can produce groundwater, but these are going to be the major ones, okay? These are the best known water producers. The easiest way to get water is to find one of these units. Okay. Now, in order to understand what groundwater is, you also have to know what it's not, okay? So, the upper unit of the landscape from the surface down to some depth is called the unsaturated zone. So we're going from the surface on down. It's called the unsaturated zone. In the unsaturated zone, some, but not all, of the pore spaces are filled with water. Some, but not all, of the pore spaces are filled with water. So you have some water in your pore spaces, but you have some air. Hence the term unsaturated. Yes?
How far down does that zone go?
It depends, and that's a good question. I'm gonna get to that in a minute. The water that's in the unsaturated zone, this is not groundwater. It is not groundwater, it's called soil moisture. Okay? So it's called soil moisture, it's not groundwater. And the reason it's not groundwater is because some of the pore spaces are filled with water, but some of the pore spaces are filled with air. You can put a well in the unsaturated zone and pump that thing all day long, and you're never going to get a drop of water out of the ground, okay? Will not happen, because you cannot get groundwater out of the unsaturated zone because it doesn't exist there, okay? Now, eventually, if you go down deep enough, you're going to get to the next zone, which is the saturated zone. But to answer your question, how deep is that unsaturated zone? The answer is it depends. It depends on where you are. In wetter climates, it tends to be closer. It tends to, well, put it this way. The line that separates the saturated zone, the unsaturated zone from the saturated zone below, which we're going to get to in a minute, is called the water table. So the question you actually asked is, how deep is the water table? In wet climates, like the Southeast, it has a tendency to be closer to the surface. In dry climates, it has a tendency to be deeper, but it bounces up and down with the time of year. In wet times of year, the water table rises, and in drier times of year, the water table goes down. So there's not a pat answer to, how deep does it go? But you can look it up on the Web Soil Survey, because that's one of the things on the Web Soil Survey. The important point is you cannot put a well in the unsaturated zone and get water out of the ground. It will not work, okay, because it's not groundwater. So what happens is, eventually, as you keep going down, the pores will become filled with water, and that takes you into the saturated zone. Okay, that takes you into the saturated zone. In the saturated zone, all of the pore spaces are filled with water. Okay, all of the pore spaces are filled with water. So there is no air in those pore spaces because it is completely saturated with water. That's the saturated zone. That is groundwater. So groundwater can only come from the saturated zone, where all of the pores are filled with water. So In the unsaturated zone, there is water, but we call it soil moisture. It's really important for plants because, contrary to popular belief, plants do not like, unless you're dealing with an aquatic plant, plants do not like to be submerged in water. They do not like to have their roots completely submerged in water because they need both water and air. So that zone of soil moisture is important for growing plants, but it's not groundwater. So we're only interested in the saturated zone. That's the zone below the water table. All of the pores are filled with water, and so this is where you're going to put your well and pump water out of the ground. Okay, now, not every unit in the saturated zone is going to produce groundwater, because not every unit in the saturated zone is going to be sand and gravel, sandstone, or limestone. You can have crystalline rock like granite or basalt. You're certainly going to have mud rock. You can have gneiss or schist for metamorphic rock. So not every unit below the unsaturated zone is going to be a water producer. Some of them are not going to produce water. So we're going to get rid of the unsaturated zone. We're not going to worry about that. But within the saturated zone, there are two major categories of units. The first one is called an aquifer. An aquifer is going to be your water producing unit. So it's a geologic unit. So it'll be made out of primarily sand and gravel, sandstone or limestone, and it is going to be able to produce water. So your aquifers are your water producing units. If I'm going to drill a well, I want to drill a well into my water producing unit. Those are my aquifers. However, there are non-water producing units in the saturated zone. It's not that they're not saturated with water, because they are, but they don't have the right combination of porosity and hydraulic conductivity to produce water. And these are called confining units. So mud rock, for example, is a confining unit. It's got very low porosity, but even worse than that, it's got extremely low hydraulic conductivity. So it's in the saturated zone, and it's saturated with water, but it will do you absolutely no good to put a well into a confining unit, because that groundwater moves so slowly that you will never be able to pump it out of the ground. So a confining unit doesn't prevent the movement of water, but it retards the movement of water. Groundwater moves so slowly through a confining unit that essentially you can't pump it out of the ground. So you're dealing with a unit with very, very low hydraulic conductivity. So things like mud rock and clay, these are confining units. Okay? Crystalline rock, those are confining units because they don't have that combination of adequate porosity and high hydraulic conductivity to actually move water through. They're an important part of the system, but they're not water producing units. Another term that's sometimes used for confining units is aquatards. Once again, because it aqua from water, tard for retards the movement of water. I use the term confining units because I happen to be a groundwater geologist, and this is the term that we normally use. But you can see, you do see terms in your book introduces the term aquatard. Some of these things are kind of going out of the literature a little bit, but an aquatard and a confining unit are the same thing. So your aquifers are primarily gonna be sand and gravel, sandstone, limestone, adequate porosity, high hydraulic conductivity. This is where you're gonna put your wells in to produce your water. Confining units, mud rock, clay, crystalline rock, very low hydraulic conductivity. Water moves so slowly, you can't pump it out of the ground. So, even if you know you're in the saturated zone, you have to know where to put your wells. And so your wells have to be in your aquifers because those are the only units that are gonna produce water. Okay, now we're gonna talk specifically about the aquifers because there are two different types and they have sort of different properties. So it's important to understand the difference between the two. The shallow aquifer, the one if you're starting from the surface and going down, the shallowest aquifer that you run into is called an unconfined aquifer. It's called an unconfined aquifer. So this is the first type of aquifer. This is going to be the shallow aquifer, and I'll come back to this in a minute. But the top of an unconfined aquifer is the water table. Okay? So the top of an unconfined aquifer is the water table. So this is going to be your first aquifer. So as soon as you hit the water table and go down, you're in your unconfined aquifer. Now, unconfined aquifers, once again, they're generally shallow, so you don't have to drill very far to get into an unconfined aquifer. And unconfined aquifers can supply, an excellent source of water. But one of the issues with the unconfined aquifer is that water tables are not stationary. Water tables go up and down depending upon whether you've had a lot of rain and water is replenishing the system, or whether you're in a dry period and you've lost a lot of water. So the water tables go up and down. So the thickness of the unconfined aquifer can change as well, depending on whether your water table is going up or going down. Which is just something that you have to be aware of if this is going to be your water producing unit. Now, the way that you actually get water out of an unconfined aquifer is through a process called gravity drainage. Okay, and you don't have to worry about the term, but basically it's like putting a straw in a glass of water and sucking on the straw. So if you put a straw in a glass of water and you suck on the straw, what happens to the water level in the glass? It goes down. Same thing happens when you put a well in an unconfined aquifer. The well is the straw, the aquifer is the glass. You put a well in there, you pump it, the water level around the well goes down. So you have to make sure that the pumping rate that you use is not so high that essentially you take all the water. You dry out your well. It would be like sucking all the water out of your glass, and so you're still left with your straw, but there's no water left in there. The same thing happens with an unconfined aquifer. When you put a well in an unconfined aquifer and you pump water out, the water level around the well drops. And so if you're not careful about your pumping rate, you can actually drop the water table below the bottom of your well, and guess what? No more water. And so you don't want to do that to yourself, but you also can't do it to your neighbors as well. You don't want to dry up your own well, but you don't want to dry up your neighbor's wells either. So that's just one of the things that you have to be cognizant of when you're dealing with unconfined aquifers, is that the water table is going to go up and down. So you have to make really sure that your pumping rate is not too high. because if your pumping rate is too high and you take out too much water, you could end up drying out your well or drying out your neighbor's well, and that's not good. Groundwater geology is, we're a bunch of math nerds, not like high dollar math. Some of them are like really, really high dollar math, like, you know, way up there in the fourth levels of calculus. Most of us just like to crunch numbers. We're like, you know, algebraic nerds. And so there's a lot of number crunching that goes on in groundwater so that we can figure out, okay, if this is my aquifer and this is its properties, what kind of pumping rate can I use to how much is it going to drop the water table? We do that kind of stuff all the time, just because we like crunching numbers. Okay, so that's your unconfined aquifer. The other aquifer is called a confined aquifer. A confined aquifer is sandwiched between confining layers. It's sandwiched between confining layers. So you might have like a sandstone sandwiched between two mud rocks. Or you might have sand and gravel sandwiched between clay, you know, on the top and the bottom. So a confined aquifer is simply an aquifer that's sandwiched between confining layers. Okay? Now, if you put a well into an unconfined aquifer and you measure the water level, okay, which is, put your well in there and then you can use there's a probe you can use and you can drop it down there and you can see where the water level is. If you're in an unconfined aquifer and you measure the water level in a well, you're actually measuring the water table. So you put your probe down there and it goes beep, beep, and that's how you know exactly where your water table is. If you're in a well in an unconfined aquifer. But if you're in a well in a confined aquifer, you're not measuring the water table. You're measuring something called the potentiometric surface. So the potentiometric surface is the water level. It's the water level in a well in a confined aquifer. It's the water level in a well in a confined aquifer. And it's not the water table. Easy analogy. Let's say I'm making myself a gargantuan water balloon, okay? I am making a huge water balloon. So I've got this thing in the sink and I've got it full of water and it's almost ready to pop, but not quite. I've got this mega water balloon. And let's say it was possible for me to take a thin tube and to put it in my water balloon without popping the balloon. Okay. So I got this water balloon that's just full of water and I'm going to put a little thin tube in it. What's going to happen to the water? Got a big water balloon, it's almost ready to pop, and somehow I'm going to put a little hollow tube in my water balloon. What's the water going to do? Is it just going to sit there?
It's going to come out.
Right, it's going to shoot out of the top, right? And the reason it shoots out of the top is because you've got a lot of pressure in that water balloon. And how much it shoots out is a function of how much pressure is in your balloon. That's how a confined aquifer works. Confined aquifers, because they're sandwiched between those confining units, they're under a lot of pressure. I mean, you've got all this stuff, sitting on top of that confined aquifer. It's got a really low hydraulic conductivity. So literally, it's just under an enormous amount of pressure. It's just like your water balloon. So when you put a well in there, it releases the pressure and the water's gonna shoot up in the well, and how high it shoots up depends on how much pressure is in the aquifer. So you're not measuring the water table, you're actually measuring the pressure in that confined aquifer because the water shoots up because it's under pressure. Okay. So I can measure my water level in that well and it's going to be somewhere, but it's not going to be the water table. Okay, it's going to be someplace, however much the water shut up in a well. The way you actually get water out of a confined aquifer is not by putting a straw in a glass of water and sucking on the straw. It's like squeezing a wet sponge, right? If you have a sponge that's completely saturated with water, if you put it between your hands, how do you get the water out of it? Squeeze it, okay? That's exactly what happens in a confined aquifer. When you take some water out of the confined aquifer, it releases some of the pressure, and the aquifer ever so slightly kind of adjusts itself, and it literally squeezes the water out one drop at a time. So it's just like squeezing water out of a wet sponge. It takes a lot more effort to squeeze water out of a wet sponge than to suck it through a straw out of a glass. But the beauty of the confined aquifer is you don't have this water table going up and down, so you never have to worry about running out of water. Your confined aquifers always stay completely saturated with water. You don't ever have to worry about drying out your wells. Okay? So they're really good for municipal sources of water. The wells are providing your whole community with water, because you never have to worry about those water tables bouncing up and down. Another name for a confined aquifer is artesian aquifer. Okay? All confined aquifers are artesian aquifers. There's no difference between the two. And any well in a confined aquifer is an artesian well. Okay? So, back to the bottled water industry. When the bottled water industry has a big label on there that says this is pure artesian water, that means it's water from a confined aquifer. It's not better, it's not worse, it's not, better for you. It's not anything. It's water out of a confined aquifer. That's what an artesian aquifer is. And you see the advertisement, from pure flowing artesian wells. Artesian wells are wells in a confined aquifer, okay? Once again, kudos to the bottled water industry, who has done an outstanding job of marketing and convinced us all that if we're not drinking pure artesian water out of a bottle, something bad is going to happen. And nonsense, it's just water out of a confined aquifer. That's all it is. Now, sometimes if the potentiometric surface is high enough, sometimes an artesian well, which is just a well in a confined aquifer, will flow without having to put a pump on it. That's if your potentiometric surface is really high. Most of the time, artesian wells don't flow by themselves. You actually have to put a pump on them and pump water out of the ground. So once again, the only difference between a flowing artesian well and an artesian well is whether or not you have to put a pump on it, okay? But it's all the same. It's all the same, and the water is all the same. It's all water out of a confined aquifer. So, the word artesian seems to make people think that it's really special, but it's really not. It's just water out of a confined aquifer. So, you should always know where your water comes from. In Mobile County, you don't drink groundwater, you drink surface water. So if you go fill up your water bottle at the water station right outside of the door, your water is actually coming from the Big Creek Lake Reservoir, which is a little bit north of here. It's a very, very large reservoir that collects surface water, and that's where your water comes from in Mobile County. Now, if you go to Dauphin Island, you're actually drinking groundwater, but it's groundwater that comes from an unconfined aquifer. Those are very shallow wells on Dauphin Island. So your water comes from an unconfined aquifer, and that water actually has to be treated because it's a little salty. It's not like super salty like the ocean, but it's salty enough that it has to be treated. It goes through a process called a reverse osmosis process, which you don't have to worry about. Essentially, you have to take the salts out of the water. The problem with having too much, and it's not necessarily sodium chloride, there's lots of different salts. The problem with having too much salt in your water is it makes it taste bad. And so there's actually a drinking water standard for too much salt in your water. So that water has to be treated in order to be used because the salt content is too high. It's actually pretty expensive to go through reverse osmosis to supply adequate water, but that's really the only source of water that they have on Dauphin Island. They don't have any big reservoir, they haven't had anything on Dauphin Island, so their best option for water is to get water out of an unconfined aquifer, but it does have to go through this reverse osmosis process in order for it to meet drinking water standards. It wouldn't hurt you, but it would taste bad, and there is a taste standard for water. So once you get above a certain limit of dissolved salts, you have to treat your water. If you go to Baldwin County, you are drinking artesian water because your water comes from a confined aquifer. It does not have to be treated because that water quality is just fine. So you can go fill up all of your water bottles in Baldwin County and you can market it as pure artesian water because that's exactly what it is, because all of the water in Baldwin County comes from, all of the public supply water in Baldwin County comes from confined aquifers. So in a, relatively short distance, 2 counties in Dauphin Island, you've actually got 3 very different sources of water. So if you're used to drinking the water in Mobile, and then you go to Baldwin County and you say, oh, that water tastes different, the reason that water tastes different is because it's coming from a different water source. And so there's lots of dissolved stuff in your water, which is not gonna hurt you, but that's what makes your water taste different, sometimes smell different, is because of the dissolved stuff in your water. And groundwater has a tendency to have a lot of dissolved stuff in it because as the water moves through rocks, it dissolves the rocks and it picks up different things. So groundwater has a tendency to have a lot of dissolved stuff in it. Once again, it's got to meet a drinking water standard, so it's really not going to be an issue, but it does have certain standards it has to meet. So that's why water tastes different, just because it comes from different sources. Okay, well, we're going to stop here for today because this is